Welcome back to this series of lessons about Tomasulo's algorithm. In this lesson I will extend this dynamic scheduling algorithm with memory accesses. Until now I have concentrated on register instructions, instructions whose source and destination operands are registers. There is a dependence between a pair of register instructions if the destination register of the first is equal to one of the source registers of the second instruction. Memory accesses are slightly different because their operands are not known until the effective address has been calculated, as I will explain on this slide. Obviously, loads and stores to different addresses can be executed out of order, but loads and stores to the same address can cause hazards, and if they do, they must be executed in order. For example, if we first store to address 1000 and then load from that address, we have a read after write hazard. Recall that register 0 is always 0 in MIPS. Similarly, if we first load from address 1000 and then store to address 1000, then we have a write after read hazard, and if we have two consecutive stores to the same address, there is a write after write hazard. The problem is, however, that whether or not a hazard exists is known only after the effective address has been calculated. Consider for instance this example. Whether or not there is a raw hazard depends on the value of register 1 at runtime. If R1 equals 0, then there is, otherwise not. That means that in order to determine if a load or store can be executed at a given time, the effective address of previous memory accesses must have been computed. I will now sketch how Tomasulo's algorithm can be extended with memory accesses. This figure shows the structure of a floating point unit based on Tomasulo's algorithm as we have seen it before. There is the instruction queue at the top, the floating point register file with the RS field at the top right, the reservation stations in the center, and the common data bus to broadcast the result to all awaiting reservation stations, as well as the register file. To support memory accesses, we need to add an address unit, loads and store buffers, as well as a memory unit comprised of a memory hierarchy. If a load or store instruction is retrieved from the head of the instruction queue, it is sent to the address unit. The address unit then calculates the effective address and, provided there is no hazard, places the load or store in one of the load or store buffers. When the value loaded by a load is returned from memory, it is placed on the common data bus and from there to any awaiting reservation station and the register file. Let me now describe how loads and stores are executed. Both consist of two steps. The first step is the calculation of the effective address, and the second step is the actual memory access. To support several in-flight loads and stores, each load and store buffer has a field A, which is the effective address calculated in the first execution step. Furthermore, each store buffer also has a value field, which is the value to be stored. The value field of a store buffer can also be the identifier of a reservation station that will produce the value to be stored. So a store can be placed in a store buffer before the value to be stored is available. For that reason, the common data bus was also connected to the store buffers in the figure on the previous slide. Finally, I remarked that a reservation station can also be waiting on a load buffer in addition to other reservation stations. For instance, in this example, the reservation station is waiting on load buffer 2. I now describe the issue stage of loads and stores. First, I consider a load. As mentioned before, first the address unit calculates the effective address by adding the constant offset to the base register. Then this effective address is compared to the address field A of all active store buffers. If there is a match, then there is a read after write hazard, since there is a previous store that writes to the same address, and the load will not be issued, it will not be placed in a load buffer until the conflicting store completes. A store is handled very similarly, but we must check for a conflict in both the load buffers, in which case there is a write after read hazard, as well as the store buffers, in which case there is a write after write hazard. In any case, this ensures that there are no hazards between loads and stores accessing the same address. A simple example to make this clear. The load instruction load double to register F1 from address 1000 plus R0 is sent to the address unit. At this point in time, store buffer 1 is active and wants to write to address 1000, and store buffer 2 is also active and wants to write to address 1004 as highlighted in red. The address unit calculates the effective address 1000 as highlighted here in green. Since store buffer 1 wants to write to the same address, there is a conflict in this case, and the load will not be sent to one of the free load buffers until the store in store buffer 1 completes. Notice that loads and stores do not have to be sent in order from the load and store buffers to the memory unit, but can be freely reordered. This completes this lesson. Thanks for watching. In the next lesson I will give a loop-based dynamic scheduling example. Hope to see you back.